Today we're going to talk about uniform circular motion. And to talk about uniform circular motion, we're going to start with this bowling ball. And we're going to talk about the motion of the bowling ball as it travels across the floor. So, um, you know, circular motion is a combination of forces acting on objects in a particular way and the idea of inertia. So inertia tells us that if an object is at rest, it wants to stay at rest. And it's going to do so unless an unbalanced force acts on it to cause it to accelerate. And if an object is in motion, it wants to stay in motion. And that's kind of like the middle school idea. An object in motion stays in motion unless acted upon by an unbalanced force. More specifically, though, and more correctly, and importantly for us to understand, is that when an object is in motion, it wants to stay in straight line motion at a constant speed, right? And that's going to be important for us here when we talk about circular motion. So let's take a look at this bowling ball. So our bowling ball is here on the floor. Now, if the bowling ball happens to be moving already across the floor, then there's a few things that we can say about that bowling ball moving across the floor. So our bowling ball is here. So if it moves across the floor, the way I'm going to get this thing to go faster is by exerting a force that is in the same direction as motion, right? So point number one here for us today. If I want to get something going faster, I exert a force in the exact same direction as it's already moving. Now, the flip side of that is if an object is already moving, in order to slow it down, I must exert a force in the opposite direction. So if I want to speed something up, I exert a force in the same direction. If I want to slow something down, I want to exert a force in the opposite direction. So those are the two choices so far that we've been talking about. Well, a third choice is that if we exert a force perpendicular to the object's motion, then it won't accomplish either of the first two things. In other words, if I exert a force perpendicular, that's certainly not in the same direction as motion. And if I exert a force perpendicular, then it's certainly not in the opposite direction as motion. So when we exert a force perpendicular to the direction of motion, then we actually change the direction of motion. We don't speed it up, we don't slow it down, we change the direction of motion. So forces that act perpendicular to motion change the direction of motion. So if we have this bowling ball here, and the bowling ball is traveling straight, again, make it go faster, make it go slower. Same direction, opposite direction. Well, what happens if instead of pushing it in the same direction or opposite direction, I push at a right angle? So if I push this way, you see that the bowling ball changes its direction. Same direction as motion, the force will speed it up. Opposite direction of motion, the force will slow it down. Perpendicular to the direction of motion, the force will change its direction. Well, what circular motion is basically a force constantly acting perpendicular to the direction of motion. Now, there's a couple fine points that we're going to talk about after we maneuver the bowling ball here. That'll be a little bit easier with a wiffle ball on a string than it will be with this. But again, how do I get this bowling ball to move in a circle? Okay, well, to get it to move in a circle, it's constantly changing direction. So if I want this thing to move in its circle, let's get it so the circle's always in the camera here. If I want this thing to go in a circle, the bowling ball in a circle is constantly changing its direction. Right? So if we think about our geometry here, this ball wants to go in a straight line. In fact, one of the things we're going to talk about in a second is it wants to go tangent to the circle. And we all know that there's an infinite number of tangents to a circle. If I want to keep this bowling ball moving in a circle, it is constantly changing its direction. Well, we exert a force perpendicular to the direction of motion in order to get something to change its direction. If I wanted the ball to go faster, then I would push in the same direction as motion. If I wanted the bowling ball to go slower, I would push in the opposite direction of motion. But I want to get the bowling ball moving in a circle. Notice I am pushing towards the center of the circle. And that's an important aspect for us. The field hockey stick here is pushing towards the center of the circle. It's supplying something that we call a centripetal force. And as we talk about this circular motion, that term centripetal force is going to be important to us. So let's talk about it in terms of a wiffle ball on a string. So let's continue our discussion on circular motion using this wiffle ball that's attached to a string. Now, circular motion, as much as any topic or unit, in my opinion, lends itself to 4 very specific goals. Much of our goals are kind of gray and blurry. We have to learn a bunch of concepts and be able to apply them in very different ways. And circular motion is much like that. We've got a basic set of concepts, and there's going to be lots of different ways that we apply those concepts. But I think that circular motion is much more straightforward in terms of the 4 main ideas. So right off the bat here, our 4 main goals here for circular motion have to do with the direction of the net force, the direction of the centripetal acceleration, and we'll get to all these terms, the direction of the velocity of an object in circular motion. So we have 3 vectors that we have to be familiar with. And then we've got to be able to use sum of the forces equals mv squared over r. Okay, so let's talk about this ball, traveling vertically or horizontally rather on a string. Okay, so like this is tough, right? You can imagine this ball traveling in a circle that's horizontal. All right, it's tough. I'm trying to make this work on a TV screen. There we go. That's kind of more horizontal. Okay, so we got this ball twirling in a horizontal circle, and that's ultimately where we're going to get to. But let's first start with the string's job. So if I hold this ball just like this, the string's got a job. The string's job is to simply hold this ball still. Now, the ball is still, so it has no acceleration, right? So the sum of the forces equals 0, right? We've got a ball here that is still. So I'm holding that ball at rest. And the tension force then, right? So if I were to draw a force diagram, here's a picture of the ball on this string. If I'm going to draw a force diagram, let's put some holes in it. There's my wiffle ball. If I'm going to draw a force diagram of that, then I've got tension going up and I've got the weight going down. And again, tension's job is to hold the ball still / balance out the weight. So when I hold this thing vertical like this with the wiffle ball, the string's got one job. Its job is to balance out the weight. Well, what happens if I take the ball, it's at rest, and all of a sudden it's moving? It's accelerating, right? Because it wasn't moving and now it's moving. So now the ball's kind of got 2 jobs. I'm sorry, the tension's kind of got 2 jobs. It still has to balance out the weight, and then it's got to accelerate the object upwards. So we progress, right? The sum of the forces in this particular case, the sum of the forces is equal to m times a. And these are the 2 situations that we've been utilizing. So instead of this ball, being still, we've got this wiffle ball that's accelerating upwards. Now, what does that do to the tension in the string? Okay, well, the force diagram is still the same, right? So I still have this ball, right, with tension going up and weight going down. But now the tension's got 2 jobs, right? It's got to balance the weight, and then it's got to accelerate the object upwards. It can't accelerate the object upwards without first balancing out the weight. So it's got these two jobs. Well, if I use my math, right, sum of the forces equals m times a, it's accelerating upwards, so I want that to be positive and that to be negative. So T minus W is equal to m times a. Over here, we know that T equals W. Why does T equal W? Because the sum of the forces is equal to 0. You know, let's make that a little bit cleaner so we have a direct comparison. Sum of the forces equals 0. T minus W equals 0, so T equals W. Relatively self-explanatory at this stage. So over here, we've got T equals W. Well, what does T equal over here? If I keep this math going, T equals W plus MA. T's got two jobs over here. It's got one job over here. Over here, it balances out the weight. Over here, it balances out the weight and accelerates the object. Well, now, we're not holding this thing stationary anymore. We're not accelerating in a line. Well, today's lesson has to do with circular motion, right? Circular motion, the string's got a different job. The string's job here is to hold the ball in a circle. Now, again, being on video maximizes like how non-horizontal this circle is. My goal is for this to be going around in one plane, right? If you could imagine a pole right here and this thing orbiting around the pole, that's my goal. So I spin this thing around. Friction's job now, or not friction, tension's job, rather, is to hold the object in a circle. So now, tension, so here's the wiffle ball. Now I've got this string that's horizontal. When the ball is out here, the string is horizontal. It's holding it in a circle. The ball comes over here, the string is still horizontal. It's holding it in a circle. So if we're drawing this as a force diagram, then the tension acts towards the center of the circle. My bad. If this is the object, then the tension is acting towards the center of the circle as this thing orbits around that circle. The string's job is no longer to accelerate up or just hold it. Its job is to keep it in the circle. Because look at, right? What if I have this string, right? The tension in the string is now holding the ball in a circle. So let's talk about that, right? This is where the inertia kicks in. What does the ball always want to be doing? It always wants to be going in a straight line. Because inertia says an object in motion wants to stay in motion at the same speed in a straight line. So if I freeze frame this thing right here, it wants to keep going in a straight line. Well, what's preventing it from going in a straight line? The tension in the string is saying, no, don't go in a straight line. Instead, come back towards the middle. So the ball wants to go straight. The tension's saying, no. If I let go of the string, there's no more tension. So the ball goes in a straight line. It goes straight up in the air. If I let it go on the other side of the circle, it goes straight down. So the ball always wants to go in a straight line. So if I'm looking at my three goals here, the direction of the velocity is the easiest direction. All right, so goal number 3, I'm kind of going to go out of order. If I've got an object and it's traveling in a circular path, let's say it's traveling in a counterclockwise circular path, then that object's velocity is always tangent to the circle. Depending on the point in the circle we are at, we obviously have a different tangent because we have an infinite number of tangents along a circle. So if the object is right here, then the velocity vector is always tangent to the circle. What dictates that it's tangent to the circle? Well, the idea that an object in motion wants to travel in a straight line, unless something prevents it from traveling in a straight line. Well, what's preventing this ball from traveling in a straight line? The string is preventing the ball from traveling in a straight line. And the string is pulling the ball towards the center. In this particular case, we say that the string is acting as a centripetal force. Now that is a new term for us, and that's really number one right here, right? So if I duplicate that same circle, then here's my object down here. It's traveling in a counterclockwise circle. It wants to go in that straight line, but the string is not allowing it. The tension in the string is directed towards the center of the circle. Now again, like mathematically, it is best for us to first talk about horizontal circles. But as I'm looking at this video, it's much easier for us to visualize this circle that's vertical. All right, so let's, for now, while we're accomplishing our three main goals here, let's switch this circle to be vertical. Okay, so if I stop this thing right here, it wants to keep going straight. So it wants to keep going straight. What's preventing it from going straight? The string is preventing it from going straight. When the ball is right here, it wants to fly towards the ceiling. What's stopping it? The string. We say that the string is acting as a centripetal force. Now that is a term that a personal goal of mine is that each year I want kids to be really familiar with this term, because kids and people in general tend to mess that up. They start saying centrifugal and then they just kind of mumble, right? Because it gets confused with this idea of centripetal force compared to centrifugal force. And that's for a different day. But for now, in our introduction here, the string is providing a centripetal force. And that centripetal force, I'm going to make this a little bit easier on us, okay? I'm going to say that let's not call that F net. Let's call that F sub C, or centripetal force. So the string is acting as a centripetal force, F sub C, that's directed towards the center of the circle, always. Now, we've got our direction of velocity. We've got our direction of force. This AC, in addition to centripetal force, forces cause accelerations. So a centripetal force causes a centripetal acceleration. Now the word centripetal, if you look it up, means center seeking. So we have this force that is pushing objects towards the center of the circle. Forces cause accelerations. In other words, if I wanted to accelerate this marker upwards, I would exert a force up. If I wanted to accelerate it in this direction, I would exert a force in that direction. Accelerations happen in the direction of net forces. So our net force, or acting centripetally, our centripetal force, goes towards the center of the circle. Guess what? Our centripetal acceleration is also directed towards the center of the circle. So our second goal would say, okay, if I've got this circle moving in or this object moving in a counterclockwise direction, if it's located down here, it is actually accelerating in that direction. Now, this type of acceleration, while not listed as one of our main goals here, because I like to keep this nice and simple, this acceleration is much different than other accelerations. See, an object traveling in a circle can accelerate even if its speed is not changing. It's accelerating centripetally because its direction is constantly changing. In other words, look at this V, it's pointed in that direction. Look at that V, it's pointed in that direction. Those two things are different from each other, even if the number associated with them is the same. In other words, if this is 10 meters per second and that's 10 meters per second, those are different velocities because they're different directions. So a centripetal acceleration is associated with a delta or a change in direction. So centripetal accelerations come from changing directions, not numbers, right? Like if I make something go faster or slower, we're changing the number associated with the velocity. Here, we're changing the direction. Centripetal force goes towards the center of the circle. Centripetal forces cause centripetal accelerations, which also go towards the center of the circle. Both of those things preventing objects from going straight. So our velocity vector for circular motion is always tangent to the circle. Now, our last thing is this. We've been talking about keywords for a long time. If a situation has an object at rest or at constant speed, those keywords default us to saying sum of the forces is equal to 0. If the word acceleration is associated with the situation, then the sum of the forces is equal to ma. As soon as we see the word circle, circle now equates us to sum of the forces equals mv squared over r. Now our last thing for the day, right? So there's our last goal. Use of sum of the forces equals mv squared over r. And this is the most complicated of the 4 goals, so we'll learn a lot about it. For us today, as soon as we see the word circle, then we know that the sum of the forces must be equal to mv squared over r. Now, last thing here. We know there's a centripetal acceleration, which is caused by this centripetal force, which is towards the center of the circle. If there's an acceleration, then sum of the forces equals ma. But this is a specific acceleration that has to do with circles. So we take sum of the forces, and it equals mv squared over r. Well, look at these two things. ma and mv squared over r. So the only thing that's changed is over here I have a, and over here I have v squared over r. Well, again, this is a particular type of acceleration. We might as well be saying the sum of the forces equals mass times centripetal acceleration, which means this centripetal acceleration is equal to v squared over r. So we got our 4 goals. If you can remember these 3 vectors, velocity is always tangent, centripetal force directed towards the center, centripetal acceleration directed towards the center. And then we are going to work on use of sum of the forces equals mv squared over r for the next few days. You're going to be in good shape with respect to circular motion.